dense structure method, a method to perform dense structure calculations. We have also already seen the plane wave method, which is related to the quasi-free electron method or model. The plane wave method is more general, but one recovers the result of the quasi-free electron model. And today the method is a different one. It is the tight binding method. So this is actually the other limit. I will come back to this. So we will discuss the tight binding method. Tight binding method. This is, again, this is a model. There are approximations. And so in physics or in solid state physics, we call it the tight binding method, but the chemist will call it the LCAO method, linear combination of atomic orbital approach. So linear combination of atomic orbital. In fact, in this approach, the eigenstate, the electronic eigenstate in the crystal are written as linear combination of the atomic orbitals. So this method, as the name indicates, tight binding, works well in the case where the electronic state in the crystal, or four electronic states in the crystal that are very localized around the atoms. So this certainly will work very well for the core electrons. And it also works well in particular for the system that include element of the first row of the periodic table, because they have 2s and 2p orbitals, which are actually very tightly bound to the atom, very localized with small radii. So, so today we will discuss this tight binding method, and we assume that the electronic state, or the states that we want to describe in our crystal, the valence electronic state, can be written as a linear combination of atomic orbitals. So this is the other limit with respect to what we have seen before. Before we were looking at electronic states which are very delocalized, with functions that are very delocalized, homogeneous, and here we look at the other extreme, that is states which are highly localized near the atoms, tightly bound to the atom. Okay? All right. So this works also for ionic crystals. In the ionic crystal, instead of writing them as linear combination of atomic orbital, we write them as linear combination of ionic orbital. That is, we consider the valence state of the ion, so with a charge. So when the atom is charged. All right, so in this case, I will write the state, the electronic state, C of R, as a sum of the atomic orbital in the crystal. So I'm going to sum here. I have a crystal, so I have a Bravais lattice. I'm summing over the vector R of the Bravais lattice, corresponding to all cells in my crystals. all my unit cells in the crystal. Then I'm summing over mu, which corresponds to the atoms, the different types of atom in the basis. So mu are the atoms in the basis. If you want, in the unit cell of the Bravais lattice. And then I'm summing for a given atom type on the different electronic orbital of beta atom, S, P, 2S, 2P, and so on. Okay, so I have some coefficient alpha of R, which is labeled by R, mu, and I, and then I have my atomic orbital. For the atom mu and the orbital type I, so 2s, 2p, or 1s, 2s, 2p, and so on. So these are atomic orbital, and they are centered on the atom mu in the unit cell R. Okay? So I'm writing my wave functions of my electronic state as a linear combination of the orbitals on each atom in the crystal. So this function phi atomic mu I are a solution of the atomic problem. That is, they are solution of the equation h bar square, gradient square over 2m minus plus the atomic potential mu of R phi mu I of R atomic is equal to epsilon mu I atomic phi mu I atomic of R. So these are the solution for a given atom centered at the origin of this Schrödinger equation, the atomic for the atom. Okay? So these are, we write the state in the crystal using as a basis or as a linear, we write them in terms of a linear combination of this atomic orbital. Okay? Clear? Alright, so now I will also, this is also the other thing we do in the tight binding method or linear combination of atomic orbital, that is, we write the potential of the crystal. For LCAO it would be of the molecule, but here we are in solid state physics, so of the crystal, so our V of R is written as a sum of the atomic potentials. So we sum over the Bravais lattice vectors of the crystal and for and on the atoms in the basis of we sum the atomic potential for the atom mu centered on that is centered at the position d mu in the unit cell, and we sum over all unit cells. So this atomic potential is centered on the atom mu in the cell R. Okay? and we sum over all of that. So the potential in the tight binding method is written as a linear superposition of the atomic potential, as the sum of the atomic potential in the crystal. Okay, so now let's draw maybe these functions, I mean the atomic function in the crystal, and I will consider a monatomic crystal for simplicity. So we have, we want to draw the potential V of R, and this potential, I'm considering a monoatomic crystal. So the atoms are of one type, and at the position of the Bravais lattice points. So I have my atoms. And around each atom I have a Coulomb potential, like this, and I'm going to sum this Coulomb potential, or this potential, atomic potentials center around each atomic site. So this is the atomic site R. I have also around the origin. So I have an atomic potential that goes to zero, far away from the edge of the atom, and I will sum all of these potentials.
Sorry.
Oh, yes?
In the general case, the
Yes.
screening effect also has to take place, right?
Yeah, yeah. If you want, when you solve the atomic problem, there is also some screening there. So, yes. However...
And more or less the total potential will have the same,
Yes.
same shape as the last time.
Okay, this is a model, and it's a model for strongly for states that are tightly bound to the atoms. So the screening is less important than in a metal. But yes, it enters. Often in the end, okay, we will derive, I mean, these are assumptions, and then we will see what we get. And it's interesting, and at the end, to some extent, one can also parameterize. That is, there will be matrix element, and one could also fit them to experiments. So in the end, we elude a little bit the problem of the screening. But yes, the screening is also there. But this is a model, so we simplify things. All right, so I have this, I'm considering this site with this potential, the Coulomb potential that goes, I mean, Coulomb potential, the atomic potential that goes to zero, far away from the atom. So this is the potential V atomic that is centered on the site R. Here. All right, now for this potential, for this atomic potential, which should be more symmetric, but okay, I guess you got the picture. I will have, in the case of the single atom at that site, I will have my atomic orbital. So the deeply bound state corresponds to the 1s state. So I will have here a 1s state with a wave function. I need a little bit more space to draw it. So it's a very localized state. It will be an S state, so it is an exponential state like that. I mean, okay. In space, you will have an S state here. So this would be my wave function phi 1s at this energy. Well, I should have drawn it a bit better, but all right. The S state. So this is the 1s level. This is the potential. And I have a wave function, 1s wave function, that is like that. And it's very localized in the atom. It's a deeply bonded state. So this is my 1s wave function, phi 1s. Then at higher energy, I will have the 2s, the n equal 2 states. So I will have a 2s states, which will be a bit more, less tightly bound, but let's say quite localized. So this will be my 2s state. Actually, we have some nodes, but okay. I'm drawing the probability density. No, okay. Let's put it this way. I will have a 2s state like this, phi 2s, and then I will have also some p states. I will draw them in grid. In the atom, in the hydrogen atom, they have the same energy. So I will do some p states that will go like this, let's say. Okay, I mean, this is an example, and I will have here some phi 2p state, and there are 3 of them. There is the 2px, the 2py, and the 2pz, corresponding to the 3 L equal 1 spherical harmonics, linear combination. Okay, so I have, let's say, this, and what I'm showing here is that this state, I consider them quite localized near the atoms. I'm exaggerating a bit, but okay, that's the representation. And now, in our assumption, we are considering as a basis to write the crystal state. We consider the set of this orbital phi r, so centered on each atom, we take the orbitals that are the eigenstates of the atomic potential. So this, okay, I should continue here. So they are centered on in each unit cell, or on each, in the monoatomic crystal, on each point of the Bravais lattice. I'm summing over all the atom. In this case, I have just one type, and then on all of the atomic orbitals. Here, what I have drawn are just the one with the lowest energies. Of course, there is an infinite number of these solutions of the atomic potential for a given R. I have all the states which are bound with energy below the zero, and in the case of potential, like the atomic potential, that is not a periodic potential, I can measure the energy of the atomic state with respect to this zero of energy. But I have not only the bond state, but I have also an infinite continuum corresponding to the unbound state with positive energies. So I have a huge amount of state only for a given atomic site. So in the end, here I have an overcomplete basis, because actually taking into account all the bond state plus all the state of the continuum which are unbound, I have already a complete basis for also my crystal state. So this is overcomplete. This is an over, if I sum over all of the atomic site, overcomplete basis. So instead of taking for an atom all the bond state and all the unbound state, the continuum of unbound state, what I will do is I will consider all sides of the crystal and I will just focus on the lowest bond state. This is physically much closer to what I will get in the end for the crystal. So I will just focus on these atomic states, on all of the crystal lattice positions, or atomic position where the atoms are.
And
so
within this framework, if we will be only considering the free electrons, then we'll get the plane wave method which we discussed earlier.
Yes, it is similar, yes. It is similar, but in that case, it's useless to consider the atomic potential. One just moves to the plane wave state. But indeed, the states of the continuum are close to the electron states.
In the plane wave method, we were talking about the bound electrons that were screening the potential, right?
This core state, the tight binding that we will use it for, as example, we will use graphene, or the carbon, which belongs to the first row of the periodic table. But it would work perfectly for core states. And the core states actually basically they are very close to these solutions, and as you will see, what we will do, what comes out from the approach is that the wave functions will be written in blur state, but using the
bound state wave.
Yes. So we will write blur state in terms of a given atomic orbital states for all of the atoms in the crystal. Because a blur state, as soon as one has a crystal, in quantum mechanics and according to Blor's theorem, the electronic states have a probability everywhere in the crystal. The Blor state, if you calculate the square modulus, because of the periodic part, you are stuck with states that have a probability in all unit cells. So this has to be respected also in the tight binding method, as you will see later, because we are describing crystal states. So, anyway, you will see that the energy is actually in the limit of, let's say, when we separate the distance, the atoms strongly, we will recover the energy of the atomic states. But the wave function will be written as a linear superposition of the wave function on the different sides, with a proper phase in order to satisfy the Blor theorem. Okay, so I'm anticipating, but this is what we will find in the end in some limit case. All right, so what we will do is that we will exploit this overcompleteness in order to focus just on a specific, we will focus on each of the R in the crystal, so we will include all the wave function, but up to a energy cutoff. So we will take the atomic state, but all those that are physically relevant for our problem. So for instance, for graphene, we will consider the 1s state, the 2s state, and the 2p state. We are guided also by the chemistry and knowing the properties of the system. So we exploit this overcompleteness to just select those that are more physically sound and that will allow us to achieve a good result, accurate result with the lowest possible number of states. So the strategy is just to focus on the lowest bond state of the atoms, but for each atom in the crystal, in the case of monoatomic crystal. So we will take only a few of these states, or only a few atomic states, but with the lowest energies. And we will focus on the bond state because we know that we are applying this tight binding method for systems where the electronic states are expected to be tightly bound to the atoms. Okay, so we will take only a few atomic orbitals. So only a few atomic orbitals, and we will take the one corresponding to the lowest bond state in the atom, lowest bond states up to a given energy. For physical reasons, we know more or less which state we need to include, and if it's not accurate enough, we can always include some more. So that's the idea. Okay, so the comment here is that this method, the LCO method or the tight binding method, will work well in the case of tight binding orbital that are not too much modified by the neighboring atoms. They will be somewhat modified, but they shouldn't be strongly perturbed by the different atom, in the sense completely different because of the presence of the other atom. So the LCO method, LCO or the tight binding method, method or model will work will work well in the case of tightly bound to the atom orbitals. So, as I said, we expect that in this case these are for systems where these atomic orbitals are not going to be too much modified by the other atoms. I mean, there will be some effects of the other atoms, but we don't expect this orbital to be completely different, I mean, to change drastically because of the presence of the other atoms. Okay, we work well in the. Okay, all right. So this is the introduction. So now we are writing the wave function as a linear combination of atomic orbital, but we are in a crystal, so we have to apply Bloch's theorem. It has to be verified. Okay, so now Bloch's theorem. It applies to the wave function C, the state in the crystal. So Bloch theorem applies to C of R. So
sorry, can I ask you?
Yeah.
So before, like in the previous model, you were only thinking of the valence electrons, right? And
Yes.
the other electrons are tightly. Now we are thinking of all the electrons in the atom.
Okay. This will, if you want to find the solution for a simple metal, you are going to use a different method for the valence electron. However, in the simple metal, you have also deeply bound core states, and this method would apply to describe both. So
Okay.
this is one thing, but it's not so interesting. In the sense, we know the energy will be similar to the atom, and the probability near the atom will be similar to the atomic state for the core state. Now, it will apply also for specific system, this tight binding method. As I mentioned, an example is systems that are made of atoms of the first row of the periodic table, like carbon, boron, nitrogen, because this state, the 2s and the 2p state, are very localized in these systems. So this method will work, for instance, to describe graphene,
Okay.
the valence electron. This is an example.
So we're still talking about the valence electron, not all the other electrons in the atom.
Yes, because these are the ones that are interesting. So, and it will work also to describe the state near the gap of some insulator like ionic crystals. However, in the ionic crystal, a starting state phi atomic, you will actually not use the state of the atom, but those from the ion, like in chlorine soda, NaCl, you will take the Na plus eigenstate and the Cl minus eigenstate as a basis. And in this case, it will work also well because these are states that are tightly bound to the ion. So in that case, also for ionic crystal, it works well, this method. Okay, so
sorry, clarify.
Yeah.
That means the important is not exactly one S and one P. It can be just S and P of any orbital.
No, they have to be. It has to. I mean, you need to know a little bit about the final system to apply this method. Like for the simple method, of course, you know that the states are very delocalized. They don't have much structure. I mean, their probability is also in the region in between the atoms. So these are delocalized states, and you know you can apply the plane wave method. Here it's for ionic insulator, for instance. It's more for insulator because, but also it works the best for those from the first row of the periodic table, because these are states that are more localized than other states further away from when you go further down to other rows of the periodic table. Like all these methods, of course you want to apply them in the case where it works best. So in insulators, if you include enough state, you will be able to describe your valence electrons also well, but you don't want to go, you don't want to describe a free electron-like system, like a simple method with one valence electron with the tight binding approach. This is going to be a recipe for a disaster, in the sense you will have a hard time to obtain a good convergence this would be crazy. So this is the other limit, and it's more for insulator. All this method can be pushed at the computational cost, of course, but you don't want to use the method in the extremely expensive way. So you choose the method according to the state you want to describe, typically the valence state you want to describe in your system. Okay, Blostium applied to T of R. Okay, so now I have to label my Bloch state with K, which is a good quantum number in the crystal because of the periodicity, and these have to be Bloch functions. Or I know I can write my crystal states as a Bloch function. So let's take the example of one atom per unit cell, and I consider the s orbital. So I'm in a system with one type of orbital, the s orbital, and I have one atom per unit cell. So let's start from there, because I want to apply Bloch's theorem on states that are written as linear combination of atomic orbitals. So take for instance one atom per cell and just the s orbital, so minimal situation, just the one and just one orbital. So the 1s orbital. So let's first consider the case k equal to 0. This is the simplest. So for k is equal to 0, the Bloch function that is made from the 1s orbital, it will be just the sum of the s orbital on all Bravais lattice sites. So for k equal to 0, I know already what is my Bloch state, my Bloch function, built from the 1s orbital. It will be just the sum over all of the sites. So I write it here as psi 1s of k is equal to 0. So I want it to be a Bloch state with k equal to 0 and built as a linear superposition of 1s orbital. So it will be just 1 over the square root of n for the normalization, sum over the lattice site, the atomic function phi 1s centered on the lattice point R. So when I do this, the result will be periodic, and I have the Bloch state with k equal to 0. So the Bloch state with k equal to 0 is simply that. And this is, of course, periodic with the periodicity of the Bravais lattice. I will just show that it's periodic. Well, it's trivial, but I will show it using the second form of Bloch's theorem, where we had that the Bloch state have as characteristic that when I translate by a Bravais lattice vector, these are, I obtain exponential aik, the Bravais lattice vector, times the Bloch state, in the sense that they are eigenstate of the translation operator. This was the second form of Bloch's theorem. So this state satisfies really satisfies Bloch theorem. And the second form was that this is an eigenstate of the translation operator. Indeed, P1s state k equal to 0 if I translate by a Bravais lattice vector. I call it R prime. I'm obtaining P1s, the same state, exponential I 0 R prime. Trivially, if I translate here, I obtain the same thing, but this satisfies the second form of Bloch's theorem. I'm just showing this because this is the form we will use for an arbitrary k, I mean k different from 0. So in this case, it satisfies the second form of Bloch's theorem for any R prime belonging to the Bravais lattice vector. This is trivial, it's periodic, and so obviously this is fulfilled. Okay? Yeah? Well, okay. So when it's a bit more interesting, it's when one goes to k different from 0. And there I'm going to do the same thing. So now I'm considering a general k inside the Brien zone, so different from 0. And in this case, the tight binding function can be written some question? So, in the general case, the tight binding function for the atom mu and the orbital of the type R, I, for a general k inside the Brien zone, it can be written as 1 over the square root of n, so the same normalization, sum over the Bravais lattice vector, exponential I k times R, a phase, which is the coefficient, and the atomic function phi atomic for the atom mu and the orbital type I at the position R minus at the position dvu plus R. So the tight binding function, this is the answer, but then I will show you that it satisfies Bloch's theorem in the second form.
Capital R sum.
And the Bravais lattice vector.
Yeah.
Or if you want, we sum over all the unit cell in the crystal. So this is a linear combination of this atomic orbital centered on the atom mu in the cell R, and the coefficient is just this phase exponential IKR. So this is an ansatz, and I will show that this is indeed a function that satisfies Bloch theorem. It's a Bloch function. So this satisfies Bloch's theorem. And to show it, it's easier to show that it satisfies the second form of Bloch's theorem. So it's easier to show that it's an eigenvector of the translation by a Bravais lattice vector for any Bravais lattice vector with as eigenvalue exponential IKR when the translation is by a vector R. So the second form of Bloch theorem, I have to show that if I translate, I make a translation, I apply the translation operator on this wave function, Bloch, that I assume to, on this type binding function. It's an eigenstate of the translation operator for the vector r prime. So r prime here is a vector of the Bravais lattice, and I'm just translating by, in fact, minus r prime, but it doesn't matter which sign we take. So if I apply this translation, what I'm obtaining with this wave function is 1 over the square root of n, sum of this phase, exponential I k times r, and here, so I'm summing here over r, and I have my atomic function here, phi, and it's centered now at this position d mu plus r minus r prime, because I translated, I added here this vector r prime, so I'm obtaining here minus r plus r prime. Okay, this is just following the way I wrote my type binding function there. So now I can make a change of variable. I can define r second prime as r minus r prime. So these are all vectors r and r prime from the Bravais lattice of the crystal I'm considering. So this is going to give me 1 over the square root of n. I have my sum, and the r here is becoming r second prime plus r prime. So I will have exponential I k r prime plus r second prime, and I will have, with this change of variable, I will sum now on the r second prime. So I can do that, and then my atomic function will be r minus d mu minus r second prime. Okay, I mean, I always use the idea is to go to an infinite crystal, but I can always do what I showed you before with the von Karman boundary condition. Take a piece of crystal with n, capital N unit cell, and apply periodic boundary condition on the state. If I do that, then I can replace my r, my sum over r here by a sum over r prime, and this is correct. It's obviously correct in the limit of n going to infinity also. So this is what I obtain, okay? And now I'm obtaining then I can take out this r prime here, so I'm getting exponential I k times r prime, and what I have that remains is just this function where sum over r second prime instead of r, but it's just the sum over the lattice vectors, so it is the same. So I'm obtaining just my type binding state here. So this is exactly what we needed for the second form of Gauss theorem. That is, if I translate my Bloch function with a Bravais lattice vector, I obtain, it's an eigenstate of the translation operator with this eigenvalue, and I recover here my state, Bloch state, okay? So it satisfies the second form of Bloch's theorem, that satisfies Bloch theorem. So this is a Bloch function, okay? Sort of. Yeah. No?
Yes.
Yes, okay, fine. All right. So this was, now we know how to write our Bloch state. So now just take the example of a system with one atom per unit cell, and I consider the 1s state, the 2s state, and the 3 state px, py, pz for the 2p states. So let's take, for instance, one atom again per unit cell, but this time I'm considering the atomic function phi1s, phi2p, 2s, sorry, phi2px, phi2py, and phi2pz. So I have 5 atomic functions corresponding to the 5 lowest energy state in the atom. So 5 atomic functions per atom. So for each K point, I'm in a crystal, I can do everything separately for each K point. So for each K, I will obtain 5 tight binding functions. So I will obtain 5 tight binding functions. So here I will have phi1s, phi2s, phi2p alpha, where alpha is x, y, and z, and they will be given by this, where here I will have 1s, 2s, and 2px, well, 2p alpha. So, for instance, for a system with of carbon with 1 atom per unit cell, I would have these 5 functions. For each orbital type, I can write a tight binding function that is a Bloch function. Okay? All right. So all right. I can start from there. And if it's not enough, I can always add higher NL functions. So it's not a complete basis. It's not a complete basis, but that is, one can construct a complete basis by taking all NL or other NL functions, but it's good enough to get the lowest state in the crystal, the lowest eigenstate in the crystal. I will typically have the valence state and the lowest conduction state with this basis for a system made out of carbon with one atom per unit cell, for instance. So not a complete basis, one can construct a complete basis by taking all NL, but it's good enough for the lowest energy eigenstate. In the crystal. All right. So now we have a Bloch state, but of course, in the crystal it's going to be a bit different than in the atom, and these Bloch states, this tight binding function, are just a basis. So if I used this function, which are already Bloch state, if I use a linear combination of them, it's continuing for a given k, it's going to be also a Bloch function. I mean, a linear combination of Bloch function for a given k will be also a Bloch function for that k. So I can use this tight binding function for the 1s, 2s, 2p orbital as a basis for my crystal state. Typically for the S state in the crystal, which will be very close to the energy of the atomic S state, it's enough just to take the S function. But if I want to have the higher state, I should mix the 2p S and the 2p X and Y state, and to use this state as a basis in order to write my crystal eigenstate. So at a given k, I need to find the solution of the crystal Schrödinger equation. So Hc is equal to epsilon c. And I have to solve this by using this basis. So in the tight binding method, I will solve this by using as a basis the tight binding function. The tight binding functions, which are Bloch states, Bloch functions. Lots function. Bloch function. Okay, so I have to now solve this, which is going to give me the eigenstate for the crystal, and I will solve this using these functions as a basis. So I will use this function, the psi mu, the phi mu I P R. Exponential R Phi, the atomic function at the position mu minus R. Okay, so I will write my eigenstate in the crystal using as a basis this function. In the case I was mentioning, for instance, with this 5 orbital, I will have here 5 basis function. So, as I mentioned before, in the tight binding approach, the crystal potential is written as sum of the atomic potential. So in the tight binding method here, I'm writing H as the Hamiltonian of the crystal, as the kinetic part here, plus a potential which will be a sum of the atomic potential. So I'm summing over all gravilattice vector and over all atom in the basis, the atomic potential mu at the position in the cell R and on the atom mu. So this is the crystal Hamiltonian in the tight binding approach. So what we will do next is that we will use also the fact that these functions are eigenstate of the atomic potential to obtain some simplification. Alright, so I write my crystal in potential this way, and I write my eigenstate as on the basis of these tight binding functions. So I sum over the atoms in the basis and the atomic orbital that I consider by my basis. I have a coefficient here, mu I, and my tight binding function for the atom mu and the orbital I. So this is what we will use in the tight binding method for the Hamiltonian and for the eigenstate. So we write the eigenstate in the crystal on the basis of the tight binding function for a given atom and a given orbital. So for the carbon and the orbital 1s, for instance, and I can include also the 2s and the 2p in the basis if I want, depending if I just want to describe the lowest energy state or also the higher energy state. Okay, I can start. Yeah, okay, I will start now. So now, as we have seen in the plane wave approach, when one expands on basis, one can obtain some eigenvalue, eigenvector type of equation to solve, and this is what we will also get in the tight binding approach. So, like with the plane wave approach, I will write H times C, and then I will multiply by the complex conjugate of a basis function and integrate. So I will use the same trick that I used for the plane wave basis, also using these basis functions. So, so as with the plane wave approach, I will calculate this type of matrix element. So I will, okay, let me write it. So what I will do is calculate this type of matrix element, mu I, Ei. So I can, the nice thing with Bloch's theorem is we can work for a given k. So we can work in a given k subspace. So I'm calculating, like in the plane wave approach, H times the crystal eigenstate. This is equal to the eigen, I impose, of course, this. So I will have epsilon k times C mu prime I prime of k r sum over mu I a mu I phi mu I of k r. So I have H C is equal to epsilon k C. This is because I want to have the solution of the Schrödinger equation. I'm writing the solution in this way. And on the other side, I just multiplied by the complex conjugate of a basis, or one of the tight binding basis function, and I integrate over all space. Okay? So this is what the trick I used already in the plane wave approach, and I'm using here for the tight binding method. So when I do this, what I'm getting, I can take out the sum over the mu I prime. What did I put? No, maybe. Okay, mu I, sorry. Yeah. Sum over the mu I. I'm getting C of mu prime I prime k r h c, sorry, phi of mu I of k r, and I have this coefficient a mu I, and this is equal to epsilon k sum over mu I phi of mu prime I prime of k r phi of mu I of k r So what I'm getting is a set of equation for this coefficient mu I, where I have some matrix element here, and I have some overlap matrix element here. So basically, in the end, I will obtain, in the most general way, case, I will obtain some matrix element H mu prime mu I times this coefficient is equal to the eigenvalue times another matrix, which is an overlap matrix, the overlap between the basis function mu prime and mu I. So here I have already an equation, and what I'm going to do I guess I will continue next time, is to simplify this matrix element, obtain obtain in terms of the eigenvalue for the atoms and some simple matrix element using the atomic function. I will be able to give an analytical form for this that we will use in the tight binding approach, and also this I will be able to simplify knowing the atomic functions. So this is the starting equation. This can be used later on to obtain this coefficient, unknown coefficient, and to obtain the crystal eigenvalue, like in the pseudo-potential method. But we have to work a little bit more to get this matrix element to simplify that. So this is what we will do next time.
So here we're not yet assuming that all the basis elements are orthonormal.
No, because it's not. We will use some of that, but we cannot. It's not like in the plane where they are orthonormal. Here, not. But we will simplify in this direction. Yes. So we will see next time what we are entitled to do from physical consideration. All right, so I think I will stop here, and we will finish next time. So it will be in a little bit, because on Thursday you will have the tutorial, on Monday you will have the midterm, and so it will be on Tuesday. The midterm correction we will give you probably near the end of next week or so.
But the tight binding lesson will be...
It will not be included in the midterm.